Hello everyone. This screencast is a part of Network Embedded System coursework. We are Group 7 and the title of our project is Emergency Response System using WANT. First, let me explain our motivation behind choosing this project. Road accident is one of the major causes of death around the world. According to World Health Organization, nearly 1.25 million people die due to road accidents every year. When you have a closer look at this problem, you can see that the response time after the accident plays an important role in saving the life of the victim. So, we have come up with a system that could drastically reduce this response time. Technically speaking, the main performance parameter of our system is the latency. Let me give you all an overview of our system. Consider a scenario where a car meets with an accident. As soon as that happens, the airbag sensor within the car gets activated and thereby we can identify the car that met with an accident. The car's location is then transmitted until it reaches an ambulance, and the ambulance acknowledges the receival of a location. Also, the same information about the location of an accident is given to the roadside unit abbreviated as RSU, which we assume is connected to the server and in turn to the hospital. Thus, we can make sure that the ambulance is indicated about the accident along with its location in minimal possible time. Now that we have seen a short intro to this topic, we will further delve into the technical aspect of the project. As we have seen before, when an accident happens, the airbag sensor is triggered in a car. For this event-based simulation, we need to perform mobility simulation to simulate the vehicles and how they commute in a map. The other part of simulation would be to establish a network between the cars in the occurrence of an accident. First off, we will look into how mobility is simulated. In order to simulate mobility, we have used Sumo version 0.30.0. It is a software tool to simulate road traffic. The main advantage of this tool is there are no limitations on the network size and the number of simulated vehicles. You can import any map of your choice from openstreetmap.org. Once you are done importing, an .osm file is created. But in order to visualize this map in the Sumo graphical user interface, we need to use its built-in programs which are used for creating network topology on which the simulation runs. One such program is netconvert, which reads roads network from the different formats and converts them to Sumo format. Now we have roads in the map, but in order to simulate things like buildings, trees, etc. present in the map, another program, polyconvert, is used, which imports the point of interest and translates them to a description that may be visualized by the Sumo graphical user interface. This is done so that the vehicles move only on the roads and not anywhere else. A Python script is available in Sumo which is used to generate a set of random trips for a given network. It chooses a source and the destination of every vehicle at random, and this information is stored in an XML file. Also, the number of vehicles that could be present in the network is decided by the user, and even the vehicle class, such as the emergency vehicles like ambulance and the special vehicles like the military vehicle, etc., can be defined by the user. Before we look into the network simulation, let's see what kind of network is implemented in this project and its technical features. Wi-Fi P is an amendment to IEEE 802.11 standard to include wireless access in vehicular environment, abbreviated as WAVE. These amendments mean that Wi-Fi P support intelligent transport systems. This standard uses dedicated short-range communication and its transmission range falls between 5.85 to 5.925 GHz. This is further split into 7 channels. One channel will contain the transmission system control and safety-related messages called control channel interval. The other 6 channels contain non-safety information which is called as service channel. The MAC and physical layer of our project would be defined by the standard. In order to simulate the vehicular network using Wi-Fi P standard, WINGS along with Omnet++ was used. This provides the framework to simulate the vehicular network. The network that is implemented monitors for the occurrence of an accident, and in the event of an accident, it sends a wave short message abbreviated as WSM, which is the packet that contains the location of the car. This packet would be blindly flooded through the network. The reason for blind flooding is the fact that since this is a safety critical application, we need to be sure that the packet reaches its destination at the earliest and not worry much about the network congestion caused by flooding. In the simulation, each vehicle is assigned a class. The class emergency is for ambulance, whereas the default class is for passenger cars. When the WSM is transmitted, each node checks its class, and if the class is emergency, it acknowledges the receival of WSM with the accident location. So, as a brief recap of what has been discussed in this section, the protocol stack implemented for our project is shown over here. The physical and MAC layer are the Wi-Fi P standards. In the MAC, CSMA-CA is used to access the channel. Blind flooding is used in routing layer, and the application was developed in WINGS. Now move on to the simulation part. A flowchart is shown here which depicts the flow of our simulation. As soon as the network is initialized, the cars start to move around in the predefined routes. When a car meets with an accident, it creates a WSM with the road ID and broadcasts it. When the received node is an ambulance, it acknowledges. If not, the packet is rebroadcasted until it finds an ambulance. The simulation parameters that we have considered is as follows. The simulation time limit is user dependent and can be changed according to one's convenience. In our case, we have set it as 2000 seconds. The transmission power of each node is 20 milliwatt and the sensitivity of the receiver is set as -89 decibel meter. Similarly, the accident start and duration is user defined, and here we have set the accident start at 75th second, meaning the accident happens at the 75th second and lasts for a duration of 50 seconds. The scenario that we have created is as follows. If a car is stationary for more than 10 seconds, it is considered as an accident. The accident duration lasts for 50 seconds, as shown in the graph here.
Now we will see how the scenario mentioned before is being implemented in the software. So this is the Vane's GUI, and the particular file over here is poly.xml from the Sumo, and this, as we have mentioned this before, this defines all the points of interest such as various buildings. And another Sumo file that we have is raw.xml, which defines various vehicle classes used in this project. We have two vehicle classes. One is V type 0, which is the default class, also the passenger class. Another one is the V type 1, which we have declared as emergency. In this case, it is the ambulance. So we have created 195 passenger cars and an additional one which is the ambulance. So all these have been defined. For all these cars, the routes have been defined. This Vanes file is where we actually detect the occurrence of the accident and we flood the network. Now, this stub is actually used to find out if there is an accident in the network or not. If the difference between the current simulation time and the last driven time is greater than 10 seconds, then we say that the network should be flooded with this packet WSM, and the current timestamp for that occurrence of the accident is also noted. Upon receiving the packet, each car compares their vehicle class with the string V-type 1. Now, if if the vehicle class is V-type 1, which means that it is an ambulance, then it says that I have received the packet and it acknowledges it. The ambulance also receives the road ID, which is the location of the accident, and it also gets the timestamp. So we can calculate jitter from this. In order to run the simulation, we need to synchronize our Sumo GUI with the Vein software. In order to do that, we run this particular Python script, which will automatically open the Sumo GUI once the code has been compiled and the simulation has started running. Now, this is the initialization file for the veins. Now, all the important initialization parameters have already been discussed before in the tabular column. So here all the important parameters like accident start and the duration of an accident have been defined. Now we will start the simulation. Here we can see that various cars have been created on top of the map that was generated by the Sumo. The accident has already occurred and the node 0 has met with an accident, and the transmission range of that node is depicted by a red circle, and all the other cars have the green circle. The car now sends the packet and the blind flooding happens in the network. We can also notice that the RSU also receives the message, and when the RSU receives the message, it acknowledges it by saying hit. Now we will fast forward the simulation to see that the other cars change routes upon the occurrence of an accident. Now you can see here that the ambulance has acknowledged with the correct road ID, and it also receives the latitude and the longitude of the car, and it also notes down the accident time. Now that we have seen the simulation, we will critically evaluate how our network performs. As mentioned before, the main parameter for our evaluation would be latency, as this application is safety critical. So we measure the latency in three different cases. Namely, the first case was when the ambulance was at around 290 meters away from the accident spot. The latency that we got was around 2.01 seconds. The second case was when the distance between the ambulance and the accident spot was more than 470 meters. The latency that we got in this case was around 4.07 seconds. The last case was the distance between the accident spot and the ambulance was more than 570 meters, and we got the latency of 10.5 seconds. In order to show that our network is reliable, we repeated the same experiment for 4 times. Thus, we have also seen that repeatability is also one of the main parameters for our network. This concludes our presentation. Thank you for watching.